It's, yeah, here's a piece of nichrome. I guess you can maybe see that's pretty thin. Get it up close so that the boards will blur out. Yeah, it's a 60 centimeter long piece of nichrome, something like that. And let's just say we put, let's put 6 volts across this. Okay. Well, what happens is that you get an electric field. So what do you think the electric field would be? I put 6 volts across that 60 centimeters piece of nichrome. Amps. Put 6 volts across it. It's a uniform piece of wire. And that's a terrible diagram. Nothing's parallel, but get the idea. And what's the electric field? Okay, again, I really recommend the introductory problem sets. I work you through the reasoning in this almost from the very beginning. Okay. Um, Field strength is volts per meter. You got so many meters, you got so many volts. This just needs to be basic intuition. And of course, you have to be connected rigorously with Coulomb's law and all the other definitions, okay? Otherwise, you're not going to be conversant with what it is you're seeing. Okay? So, there'll be free electrons within there. And this comes down to conduction biology. You can read about it. In a metal, you have basically energy bands, and in the high energy bands, the electrons are extremely loosely connected to individual molecules. So you have this conduction band of electrons that get to move more or less freely through the material. Now, they don't get to move exactly freely. It's like a wave phenomenon that interferes when it encounters the atoms and molecules and so forth, okay? And electrons interfering with electrons, so there's resistance. And nichrome is alloyed such that you have a significant resistance. Nichrome is your typical heating wire and heating elements. Okay. And we could, talk about the advantages and disadvantages of nichrome and all the ins and outs and so forth. Don't want to get that deep into it, but there are free electrons, okay? and they're accelerated. So let me just say, what's the acceleration of an electron? Okay, so get a very quick result here. It's the force on the electron, which is E, the charge of an electron, or let's say Q sub E, just to be. Charge of an electron over mass of an electron. Times 10 newtons per coulomb. What's the charge on an electron? Uh, it's a great big acceleration. An acceleration that would get you up to the many multiples of the speed of light in a second. Okay? Because if you just look at the numerical, uh, that's like 10 to the negative 19th, that's like 10 to the negative 30th. So this is like 10 to the 11th times 10 is 10 to the 12th. So it's on the order of 10 to the 12th meters per second squared, and the speed of light is only 3 times 10 to the 8th meters per second. So in the order of 10,000 a second or so, you'd be up to the speed of light. Well, there's a lot of stuff within this conductor that prevents the electron from getting up anywhere near the speed of light. Okay. So the electrons don't actually end up moving that fast. I mean, yeah, they do. They move fast. They're moving 1,000 meters per second just because of thermal energy, 3/2 kT type thing. Okay. And they're just basically bouncing around in every direction. They hit each other, they bounce back. And yeah, they don't exactly hit molecules, but they interfere with molecules. They can be reflected and deflected. And so they're just all over the place. The idea is you get an electron cloud. The individual electrons get accelerated just for a very brief, nanoseconds, picoseconds, okay? You can work this out. But the bottom line is the electron cloud migrates along the wire. Okay. Now, how many electrons do you have in this wire? Well, you have electrons that are bound to the nichrome, nickel and chromium atoms, and the ones that are more or less free to migrate and to drift. Okay. I say migrates, drift is probably the better word. It's the more standard word. So I'll just say the electron cloud reacts in response to the electron field, to the electric field. And the drift velocity, the velocity with which this cloud drifts from one end toward the other, is proportional to the field. This means if we went to 12 volts, we'd have twice the field, right? Instead of 10 volts per meter, we'd have 20 volts per meter, or 20 newtons per coulomb. And we get twice the drift or twice the current. Amount of charge drifting past a given point per unit of time. For given material, let's talk for current. The current density is J, which is current per cross-sectional area. It's actually a vector. It's in the direction of your wire. I'm not using the vector notation here because the direction is implicit. If you have a bigger chunk of material where you have various sources of potential, then you have more complicated currents that can take place within a conductor. And you want to have the J vector, okay? Okay, so you have these two simple relationships. Current is your current density times the cross-sectional area. So now say I'm given two nichrome wires. Given diameters D1 and D2. Same length, same potential difference. In other words, it's like maybe we have a source down here. And here goes one wire. And here's the other wire. So they're kind of in parallel. So that's just a quick schematic. Just imagine we've got One of these is a wire of diameter D1, the other has a diameter of D2. They have the same potential difference because they're, they both have a direct connection to our source. Okay. What's going to be the ratio of the currents?
It'd be D1 over D2,
Could be.
whichever one is thicker diameter would have less current.
Well, you don't have to make a decision about which one's bigger. If you want to do I2 over I1, it's what it is, okay? That sound right?
Yeah.
Okay, so how does that go back to current density?
Not a per unit of area.
Yeah,
The surface area of those two wires is just equal to the ratio of the surface area of those two wires is just equal to the ratio of the wires.
no, I mean, that's, the reasoning steps are good, but there's a terrible wrong premise in there.
Smaller the diameter, the lower the density, or the greater the density. Yeah, the smaller the diameter, the greater the density.
The
So
current density is going to be determined for given material. Maybe I didn't say this. Let's see here. Yeah, there's a premise that I didn't think to include here.